In this video, we're going to continue on the theme of Linux file I/O, but move past open and talk about actually reading and writing files. So the learning objectives here, we're going to discuss reading and writing files. We're going to learn how umask influences file permissions that we've talked about that Linux has and uses today. And we're also going to get an introduction to a really useful tool that we're going to use throughout the semester called strace. So in terms of reading file content, once you've got that file descriptor from open, you can use it with read very similar to the way you'd use the file handle that you use with fread and buffered I/O today. The return value from read is going to be the number of bytes read or -1 on error. And if there is an error, it's going to set error no, and this relates to the discussion that we talked about in previous week's videos regarding Linux error handling. If there is a return value less than count, that means that there's no more bytes available now. So this would be if it's less than count but not negative. So some reasons that there might not be any bytes available now would be maybe you've read all the way to the end of the file, or maybe your read got interrupted by a signal like the signals that we talked about in previous weeks. I've got a really simple example here that's linked from this lecture slide that you can go over that illustrates a combination of create on open and also the functionality of read related to returning when there's no bytes available to read in the file. So this is a really simple application, just tries to read the first byte of a file, but if the file doesn't exist, it creates it with 0 size. So this can help us just kind of investigate how permission handling is handled relative to open, and also how read deals with files that are 0 length. So one of the things that you notice if you look at this code and if you try to run it, if you run it with no file, so the application is going to try to operate on this empty file based on the parameters passed in the run empty file script. And one of the things you'll notice is, despite the fact that I'm opening it here with read, write, and execute permissions for others, if you look at the empty file permissions on your for the file that gets created in the open step on your VirtualBox VM or on your Linux machine, what you'll notice is that the write permission is actually missing for the others group, even though we've specified it here in the open permissions. So what happened to that write permission? It was actually cleared by the umask. So that begs the question, what is umask? And umask is really just a per process way that you can restrict the permissions set on files. And so if you can basically make it so that even if an application is trying to open a file with some set of permissions, you're going to, as a system administrator, restrict the level of permissions that a person could give by default from that process on any files that were created. So there are reasons why you might not want a default application to be creating files that anyone could write. And so by having the default umask set to 0002, what this essentially does is a bitwise invert, or a bitwise mask off of the bit 2, which of course would be the write permission. So this is a way that you can set for processes, don't give new file creation permission for write by default using umask 2, and that happens to be the default for Ubuntu, and so that's why we're seeing this particular behavior. So what would happen if I change my umask to 3? Then instead of just masking off the write bit, I'm also going to mask off the execute bit. And so if you can use the umask command to do this, and when you do, you'll see that creating that empty file results in neither the write nor the execute bit set cleared, or neither the write nor execute bit set. One other thing I wanted to introduce here, now that we're talking about a little more about the interaction between kernel space and user space, I want to introduce the tool strace. And this is a really useful tool that we'll be using throughout the semester because it helps us see exactly what's happening between user space and kernel space. So it's kind of like a protocol analyzer for the system call traces that are happening from user space, showing you exactly what's getting called and what's getting returned from the kernel. So if you run strace with the read file execution application that I mentioned earlier and the parameter empty file, you can see that the open command, so open at in this case, the actual system call for open, is occurring and it's returning 3. So 3 is going to be our file descriptor. And then you can see the call that's going to check the file for content. There's a read on that same 3 file descriptor that we opened here in the previous step. And you can see that it's returning 0 bytes. So one thing to know about this is this did not require any source code for read files. So this could work on any application, including just a binary that you got from a closed source application, for instance. So it's a really useful tool that we'll use throughout the semester, and it can help illustrate how the interaction is working between user and kernel space. So in addition to file data, we can also use the open command with FIFOs or pipes. And FIFOs or pipes have additional option of O non-block, which can be used to open in non-blocking mode. And when you use in non-blocking mode, rather than the default behavior for a FIFO or a pipe, which is to block, waiting for access or waiting for data from the pipe, you'll get a return of E again to mean that there's no data available, which you can then pull from your application to wait for data available. So there's an example of this, creating a pipe and using this with read file. That's also in the link attached to this slide deck. And what you can see if you run this example, you'll have, if you start one thread, you'll see that by default it's going to block waiting for access to the pipe that's created in the current directory called pipe. If you open another terminal window and you just echo anything, write anything into that pipe, you'll get the response and the application will come back with the byte that was written into the pipe. So that's the default behavior that you get without specifying O non-block. But if you specify O non-block, what you'll see when you run this example is that instead of blocking and waiting for this command to be executed from the terminal, you'll get an E again returned back from read, indicating that there's no data available to read, and you can just call read as many times as you want. So we've talked about reading files and some of the modes related to read access. You can, of course, also write a file, and this again is going to look really similar to what you do with fwrite, where you're going to specify the file descriptor and then give it a buffer and the size of bytes to write, and it's going to return the number of bytes written. One thing to note, and I've mentioned before that there are options for synchronized operation on the mode option for open. So synchronized I/O becomes important when we talk about write behavior. By default, write, it does actually, if you write to a file and that file is ultimately located on disk, one thing that might be a little confusing is that when you complete the write command, and let's say the write command completes successfully, that does not actually mean that the bits were manipulated on disk. So what that just means is that you've written it into a buffer somewhere in the kernel, and it's intended to be destined for the disk ultimately. So why would we do it this way? Why wouldn't you wait until the write returns with success and actually is written completely out to the disk in order to know that that was successful? Well, the main reason for that is because disks are slow. So relative to your program, seek times on a spinning hard drive, for instance, are in probably tens to hundreds of milliseconds, which is an eternity when you're talking about code running on a gigahertz processor. So that's really the main reason that by default you won't have writes waiting for data to be written to disk. But we can control this when we're opening based on how we flag for synchronized I/O. So if we don't use synchronized I/O, which again is the default, when would it be a problem if we hadn't actually flushed all the file content to disk? This would be a problem on unclean shutdown, because we might have an application that thinks that it wrote successfully to, some output to a file, maybe updated some other thread or some other application, or wrote something out to the internet that said some action was performed on its local file system. But then let's say we lose power, and we lost power before the kernel had a chance to write the content in its buffers out to disk. Well, in that case, there'd be a mismatch, right, between whoever was notified about the state of the file on the local file system and the actual state that's going to be on the disk the next time you boot up. So how can we manage this risk? We really have to know about it as application programmers, and we have to know that we need to do a synchronization on specific steps where it's important. And there's different ways to do synchronization, there's fsync, there's fdatasync, and there's also osync, which is the option that you could pass into the open command. There's also an option where you can configure disk write caching to set the rules about when a write from disk is reported as successful relative to when it was actually physically written to the media on the disk. The Linux System Programming Chapter 2 also talks about the sync command as one way to do this, but it mentions that you typically don't want to use this for performance reasons. And the reason is where fsync and fdatasync are going to work on a file descriptor, sync is just going to work globally and tell the OS to synchronize everything. So what that means is that any application that's writing to a file descriptor that is not synchronized is going to try to synchronize all those files at once. So you can imagine that that would be a pretty heavy performance penalty.